Welcome to this Software Architecture Q&A series. In this series, we'll explore real-world architecture questions, practical solutions, design patterns, best practices, and interview scenarios. Whether you're preparing for an architecture interview or looking to strengthen your software design skills, you're in the right place. Let's build better systems together. What is software architecture? Software architecture is the high-level structure of a software system. It defines the major components of the system, how they communicate with each other, and the key principles that guide how the system is built and evolved. In simple words, think of software architecture as the blueprint of a software application. A good architecture helps us build systems that are scalable, maintainable, reliable, secure, and easier to change. So, software architecture is about making the right structural decisions early, so the system can meet both today's requirements and tomorrow's challenges. What is the difference between architecture and design? Architecture focuses on the big picture of a software system. It defines the overall structure, major components, how they communicate, technology choices, and important quality attributes like scalability, security, and performance. Design focuses on the details. It explains how individual components or modules are implemented, including classes, methods, algorithms, data structures, and design patterns. For example, architecture decides whether to use microservices or a monolith. Design decides how a specific service, class, or method should work internally. So, remember this simple rule. Architecture decides what and why. Design decides how. What are the key responsibilities of a software architect? A software architect is responsible for defining the technical vision and overall architecture of a system. First, they define the architecture vision, principles, and long-term technical roadmap. Second, they make important technology decisions, choosing the right technologies, frameworks, and tools. They also ensure the system is scalable and performs well under expected workloads. Security, reliability, availability, and fault tolerance are also key responsibilities. A software architect identifies architectural risks early and defines strategies to reduce them. They guide the development team by providing technical direction, mentoring developers, and promoting best practices. They also document and communicate architectural decisions clearly. Most importantly, the architect ensures that the technical solution supports the business goals and future requirements. In short, a software architect builds the right technical foundation today for a scalable and successful system tomorrow. What is a monolithic architecture? A monolithic architecture is a single, unified application where all major components are tightly integrated and deployed as one unit. For example, the user interface, business logic, data access, and other application components are packaged together and typically share the same deployment. The main advantage is simplicity. It is easy to develop, test, understand, and deploy, especially for small applications or MVPs. However, as the application grows, it can become harder to maintain and scale. Even a small change may require rebuilding and deploying the entire application. So, monolithic architecture is often a good starting point for small applications, small teams, and simple requirements. In short, one application, one codebase, and one deployable unit. What is layered architecture? Layered architecture organizes an application into separate layers, where each layer has a specific responsibility. A typical layered architecture has 4 main layers. The presentation layer handles the user interface and user interactions. The business logic layer contains the business rules and application logic. The data access layer manages communication with the database and handles data access operations. Finally, the database layer stores and manages the application's data. Each layer communicates with the appropriate layer below it and provides services to the layer above it. The main benefits are separation of concerns, maintainability, testability, and scalability. In short, layered architecture keeps an application organized by giving each layer a clear responsibility. What is clean architecture? Clean architecture is a software design approach that organizes an application into layers, with the most important business rules at the center. The core idea is separation of concerns and keeping the business logic independent from external technologies. At the center are entities, which contain the core business rules. Around them are use cases, which contain application-specific business logic. Next come interface adapters, such as controllers, presenters, and gateways. Finally, the outer layer contains frameworks and drivers, such as the user interface, database, web frameworks, and external services. The most important rule is the dependency rule. Dependencies should point inward, toward the core business logic. This makes the system easier to test, maintain, and change because the business rules do not depend on the database, UI, or framework. In short, clean architecture keeps the business logic at the center and external technologies at the outside. What is microservices architecture? Microservices architecture is an approach where an application is built as a collection of small, independent services. Each service focuses on a specific business capability, such as users, products, orders, payments, or notifications. These services communicate with each other through APIs, such as HTTP, REST, or gRPC. One of the biggest advantages is independent deployment and scaling. If the payment service needs more resources, we can scale that service without scaling the entire application. Microservices also provide technology flexibility and better fault isolation. Different services can use different technologies, and a failure in one service does not necessarily bring down the entire system. However, microservices also introduce complexity, including network communication, data consistency, monitoring, deployment, and infrastructure management. So, microservices are especially useful for large and complex applications that need to scale and evolve rapidly. In short, break a large application into small, independent services that work together as one system. What are architectural patterns versus design patterns? Architectural patterns define the high-level structure of an entire software system. They describe how major components are organized, how they communicate, and how the system is deployed and scaled. Examples include layered architecture, microservices architecture, event-driven architecture, and hexagonal architecture. On the other hand, design patterns solve specific, reusable problems within a particular part of the application. They focus on classes, objects, and their interactions. Examples include singleton, factory, observer, strategy, and builder. So, the key difference is, architectural patterns define how the system is structured as a whole. Design patterns define how specific problems are solved within that system. In simple terms, architecture is the big picture. Design patterns are the building blocks used to solve detailed problems. What is separation of concerns? Separation of concerns is a software design principle that divides a system into distinct parts, where each part focuses on a specific responsibility. For example, in a web application, the user interface, business logic, data access, authentication, and logging can be separated into different components. The main goal is to ensure that a change in one part of the system has minimal impact on other parts. This makes the software easier to understand, test, maintain, reuse, and scale. For example, if we change the user interface, the business logic should not need to change. In short, separate the concerns, give each component a clear responsibility, and keep the system easier to evolve. What is loose coupling and high cohesion? Loose coupling means that software components have minimal dependencies on each other. For example, components can communicate through interfaces or abstractions instead of depending directly on specific implementations. This makes the system easier to change, test, maintain, and scale. High cohesion means that a component or module focuses on one well-defined responsibility and its functions are closely related. For example, an order service should focus on order-related operations rather than handling authentication or email notifications. So, a good software design aims for loose coupling, components know less about each other. High cohesion, related responsibilities stay together. Together, loose coupling and high cohesion make software cleaner, more flexible, maintainable, and easier to evolve. What is AI architecture? AI architecture is the blueprint of an AI system. It defines how data, models, infrastructure, and applications work together to deliver intelligent solutions. A typical AI architecture starts with data sources such as databases, files, APIs, and real-time data. The data then goes through data ingestion and processing, where it is cleaned, transformed, and prepared. Next comes the model layer, where machine learning or deep learning models are trained, validated, and evaluated. Once the model is ready, the serving layer deploys the model and provides predictions through APIs or other interfaces. Finally, the application layer integrates AI capabilities into products such as chatbots, recommendation systems, fraud detection, and predictive applications. AI architecture also includes monitoring and MLOps to track performance, manage models, and continuously improve the system. In short, AI architecture brings together data, models, and infrastructure to build scalable, reliable, and intelligent AI solutions. Thank you for watching this software architecture Q&A series. There are many more interesting architecture questions and concepts coming your way. If you found this series helpful, please subscribe, like, and comment below. Share this series with your friends and fellow software engineers.